Good afternoon. I want to thank the Green Bank Observatory for inviting me to give this talk. It's been 17 years since I was in Green Bank and thought about this project. So going through my slides, I was reminded of a lot of things, and so I kind of changed the scope of the topic to match more what I think people would be more interested in, some of the interesting stories that occurred during the construction. I'm always reminded of Bob Hall, the project manager, always used to say, this was not for the faint-hearted, and I think that people will agree he was probably right about that. That looking back, there were a lot of near misses. That it's kind of a miracle that the thing got built. And so you probably know the story of how the GBT was funded, but this is for the groundbreaking. And Senator Byrd, of course, he looked at these things as campaign stops. He would use local musicians, and he would actually sing at these things. Over here in the back, there's a very interesting story of folklore about how the $75 million appropriation came about. I don't know this for a fact, so maybe George Seilstedt will tell that story. It would be interesting if he would. Back here are the people from photosynthesis, the people that made the documentary of the construction of the GBT. I think they're going to show a section of that at this conference. Over here is Bob Hall, who's the project manager. He's a very interesting character. He had been a captain in World War II, and after the war, he developed polio. He was actually treated by Dr. Salk in Pittsburgh. And he said, Dr. Salk one day told him, says, Bob, you've killed a lot of my monkeys in the lab down there with your case. But he recovered and went back to work, and he worked for Chicago Bridge and Iron, designed the steel for the United Nations building. He later worked for Roar Aircraft, which mainly they were doing antennas, broadcast at towers and so forth. And then somehow they got into the microwave business and the dew line, and he told stories about working on those things. And then he got involved in antennas for radio astronomy. He was involved in practically all of the radio telescopes at that time. A lot of antennas for JPL. He's incorporated in the history that JPL wrote a history of their radio astronomy work, and he's got a chapter in their book. But the GBT was his main goal. That was his final project, and he wanted it to be right. This was the pamphlet from the groundbreaking, and won't bore you with a lot of details, but you see the plan was very ambitious. The schedule, 1995 was the first astronomical use. Construction was going to be finished in 94. We didn't quite make that. So this is kind of a personal photo, but right after the groundbreaking ceremony with all the dignitaries and everything, it's kind of like after the circus comes to town. Immediately after the ceremony was over, everything was packed up and hauled away, and it was like nothing left except the marker where the center of the telescope was going to be. The next morning, the excavators and all were going to move in and start digging, so we decided to have a cookout at the last opportunity in the center of the Pendle Room. And this is various members of the metrology group that I was with, and the friends of the metrology group. You'll probably recognize some of these people. The metrology group was located, our labs were located in the old 300-foot telescope building. As you see, we had a picture window, literally, overlooking the project. We also had a scanner radio tuned to the contractor's frequencies. And so basically, we had a ringside seat to everything that was going on. We passed by it every day, going down and back, plus heard all the crane operators talking as they were doing the various operations and everything. So it was really quite interesting. We had kind of a great sidewalk superintendent position there. Okay, getting to the actual construction, this is the pennel bearing. This is the pennel room to support the pennel bearing. It's a huge slab of concrete here, and you may wonder why was it so big? Because the weight was actually carried by the track. Well, actually, this was sized to carry the horizontal load, from particularly the wind load. It was literally to keep the telescope from being blown off the tracks at I think it was a 90-mile-an-hour wind was the requirement. So you've got this huge pedestal buried in the ground just to keep the telescope from blowing away. This is the foundation for the track. Now, at the time, the estimated weight of the telescope was 12 million pounds. It kept creeping up and creeping up as it went, and later I'll show you when we weighed it, it was 16,727,000 pounds. So the weight had increased considerably. But the foundation, the wall looked like a T structure, where this is the bottom of the T. And after they had poured this, they decided to make the vertical portion actually wider than it is at the top. So they added another foot to the vertical section down near the bottom. Don't believe that shows up quite here, but another thing was the specifications called for the specification called for the foundation to go down to the shale. There's the layer of soil and then the shale down about 15 feet, I think it was. But it did not say that they had to be uniform, just down to the shale. Well, the contractor, Radiation Systems Incorporated, RSI, that was the initial contractor. It changed hands a number of times. They kept getting bought by other companies, Comsat and Vertex, and I forgot who the last one that bought them. But anyway, it changed hands a couple of times during the process, but the crews all remained the same. They left this project alone, even though they bought the parent companies. But they made the track even all the way around, which turned out to be fortunate because of the symmetry. If different parts of it had been different thicknesses, you'd have a different spring constant, so to speak. But as it turns out, it's uniform all the way around, and that was just a fortunate thing. Notice these grade beams. There's still 4 grade beams exposed that you see, but there's 4 more underneath the ground that you don't see anymore. This was really designed to be a sturdy pennel room, to, like I said, to take care of the horizontal load of the wind on the telescope. After the project was winding down, we scavenged some pieces from their scrapyard before they were all hauled away. What we got here is the 2 largest and smallest pieces of structural steel. You see the bottom one there is 2-inch thick plate, 36 inches square, and the lightest part is 8-inch tubing. So when you're up on the very top of the telescope, that's what you're being supported by, something that looks almost like a beer can. One interesting aspect from the metrology standpoint is the wheel system. there are a number of features here that might go undetected, but when the wheels were turned at the factory, they were cut on a taper so that the wheels are actually cone-shaped. If you were to just have one of these wheels and rolled it around, it would naturally roll in a 105-foot radius. So there's no steering needed to keep the wheels in line. And the way that was set up, on the end cap of the wheels, there is, right here, you take this cover off, the shaft is actually bored out all the way through. And in the pintle room, there were openings. There were 4 openings that were left in each quadrant, one in each quadrant of the pintle room, and the door opening. And so you could slide a alignment telescope into the bore of the wheel, which put it right on the axis of the wheel. You sight through the telescope into the pintle room to a point that's at the same elevation as the track and in the center of the pintle room. And the pintle room, in the floor of the pintle room, there's a brass marker with a punch mark in it. That's the main coordinate that the telescope was built by. Everything worked from that brass benchmark inside the pintle room. So the way they set this up, they put this truck up here, and they align the wheels to hit that target at track elevation in the pintle room. And there were some adjustments that could be made to get that line perfect. Then the same thing with the other truck. Then when they built the corners, they put this big weldment on top of that, and this is sitting on basically spherical bearings. This is just basically like a crescent-shaped male and female part that this just sits down on. And the weight of the telescope holds it down to the trucks. This is called the wiffle beam. And if you notice, well, let me go one other thing. The suspension for the wheels was very critical. You could not have springs or anything in the wheels because that would affect the pointing of the telescope. So the wheels, in effect, control the pointing of the telescope. And so you don't really want anything like shock absorbers or springs that could change. On the other hand, you want it to accommodate some motion in case it runs over something, like, for instance, a 1-inch round disc, which we tested inadvertently. So there has to be some compliance in the system to be able to move without breaking things. So the suspension is based on these flex plates that are purely in tension, or purely in compression, excuse me. And this allows the wheels to wobble back and forth and flex these plates, but it doesn't change the height of them. And at the same time, with these spherical bearings, one end can raise up and the other one drop down or whatever and pivot on this line between this bearing and the one on the other side. There was a tight specification on how much you could misalign, like when you lift one of these to service it. They didn't want a lot of twist in this corner weldment. And so the bottom line is it's proven to be a very good system. When the wheels were first aligned and placed on the track, Bob was very concerned about the taper, to make sure that it had this 105-foot radius taper. And so he asked us if we could measure the taper on these wheels in place. And so after some head scratching on how do you tell if the tilt is due to the track or the wheels, make a long story short, we did come up with a method to actually measure the taper of the wheels. And it turns out one of the wheels was out of spec. 15 of them were good. One of them was out of spec. It had to be removed. They had to put the telescope up on blocks on that corner pull the wheel out, send it back to the factory, have it returned, and brought back. Fortunately, this was found early on while they were still building the Alidade, and it didn't cause a big problem because normally they had to turn the telescope as they were erecting the steel. They had to rotate the telescope underneath the crane. So it turned out to be quite fortunate that we caught that early, and they were able to leave it parked. Okay, we're at the point here where we're getting ready to put the elevation shaft in, but let me back up some things that happened prior to that. According to the finite element model, they knew how much these towers were going to deflect under load. So with no load, they wanted these towers, I think they were something like an inch apart, an inch longer or more space than the shaft. So when the shaft was actually completed and put in, they had to use a jack and pull the two towers together in the unloaded position. And the idea being, when the rest of the telescope was completed and the loads were all redistributed, the thrust load on the bearings would essentially be zero. One of the things that happened, and I don't remember exactly the details, I wasn't involved in it, but one of these members got out of alignment during the welding and construction. And so they needed to literally bend one of these members to get it back into the proper alignment. So one weekend they had a specialty contractor came in, and he actually bent this big member back into the proper alignment by heating it. They differentially heated the thing, and then while it was hot, they locked it in place with shims, and then as it cooled, it stretched that part that had been heated, and so it wound up staying in place. Knocked the shims out, and you're back where you. I'd never heard of this before, but apparently it's common in bridge work and so forth. Another thing is, unfortunately, prior to this, while they were building this leg on the right side, the side with the elevator, there was a terrible accident, and one of the iron workers was killed, fell to his death. If you get off the elevator and go down one level, there's a memorial from the iron workers welded into the telescope there. Now this picture is out of sequence, but I wanted to show you the derrick, the S70 derrick that lifted all the heavy pieces. Just after they had finishing the elevation shaft, which was one of the heavier lifts that this derrick would ever lift, right after they finished that, within a day or two, they went to lower the boom on the derrick, and with a machine like this, the operator is actually out of sight. He's in a cabin down here on the ground, can't see anything. And so they depend on people to give him directions and tell him what to do. And so the winch room was back here on the back side of the derrick. And anytime they did anything, they sent an iron worker to watch the cables to make sure that everything was performing properly. And when they went to lower the boom, slack developed in the cables that goes to this block and tackle arrangement up here. And so they immediately stopped and said, oh, something's wrong. We're feeding out cable, but it's not taking up the slack. And the boom didn't come down. So the boom stuck up, slack in the cable, something is obviously jammed. So they went up there, and what they discovered was that this derrick had been reconditioned just prior to being brought to Green Bank. But apparently, in the reconditioning, there was a foul up in some of the bearings on one of the sheaves, and what they found was that the sheave had wobbled or something, and the cable actually got off the sheave and was jammed in the block, which could have easily, under load, that would, so you had maybe 20 cables in this block and tackle arrangement. If one of them became jammed, all of a sudden, maybe 2 or 3 cables were carrying the whole load, and based on just being a jammed cable, which could slip or break. It's conceivable that the derrick could have collapsed when they were putting that elevation shaft up and come down on the telescope and the crew. I mean, it could have been a disaster. So that was another near miss. Here you see things progressing on what's called the box structure, the part that rides on the elevation shaft. Now, I mentioned earlier that the center of the telescope was determined by this place in the pintle room. Well, there was a plumb bob on a music wire that was hung from the alidade that hovered right over that point on the in the pintle room that determined the center of the telescope for the surveyors to keep their benchmark. So everything was built based on that point in the pintle room until it became covered and you couldn't see it. Now you're starting to see the bull gear being added in these diagonals. So while this was going on, building the box structure it was called, there were other parallel things going on. Over here you see the top of the feed arm. The top of the vertical feed arm is being fabricated down here on the ground on solid anchor points, so that this would be pre-outfitted with the actuators for the subreflector and so forth. And here you see the subreflector being put together. Over here, the backup structure, the part that holds the panels, the reflector panels, is being built. And right here, this tower, right up here is where the surveyor worked. This would be the vertex of the telescope, of the reflector. So the instrument man sat up here at the vertex and directed the alignment of the backup structure. Now you see the box is beginning to take shape. There's still one more layer to come out of the paper, but it's taking shape, and the bull gear is being installed still, and you can see the beginning of the horizontal feed arm where it's going to go out to the left here. The bull gear is an interesting arrangement also. A lot of thought went into the design of this. The bogie that drives the gear, the pinion, is actually pivoting on an arm back behind here that you can't see. So this is actually on a lever arm, and it rides on the gear itself with these cams to keep it the transverse motion. And there's another cam you can't see here that rides on the gear itself, on the top part of the gear. It's not a good view, but the gear is wider than the flange that's holding it. And so they had this elaborate procedure to align in and out on the bull gear with shims and so forth that fit under here. And so this thing was lined almost perfectly until they actually operated the telescope, and what they found was that the gears shifted circumferentially. The design was very big on the radial control, but it kind of ignored the force on the gear, and so this all had to be redesigned. The mounting mechanisms, and I don't remember exactly how they did that. I wasn't involved in that part once we determined what the problem was. But they had to add some additional fixturing there in order to hold the gears in the circumferential direction. Here you see they're bringing in another part of the horizontal feed arm. They'd build these modules out in the field and then bring them in fly it in, as they say, to where it has to go. And then by careful alignment, the surveyor kept very close alignment on this. They would bring in the extra pieces and fill in a box. Here you see some more of that. They're just about, this will complete the horizontal feed arm arrangement. Now, some of you know John Payne. John was he was instrumental in a lot of the ideas in this telescope. But one of the things that he was particularly concerned about was the damping coefficient. Um, the structure was all welded, which was very good from a accuracy standpoint, in that there'd be no hysteresis and no joint slipping with time and so forth. So everything is welded. But that also means that there's nothing really to dissipate the energy. And so John was really concerned about the thing ringing like a bell. And so he convinced Bob Hall that he needed to run a test, because they had estimates for what the damping coefficient was. In other words, if you pluck it, how long would it take for it to ring down to an acceptable level? So he convinced the project manager to let him run an experiment. So he built this shaker machine. It's a hydraulic cylinder with maybe 1,000 pounds of weight on it, and it would oscillate back and forth. He was going to drive, and this was put up on the what they call the dance floor, the top of the elevator there, near the elevation bearings. So he convinced them to weld this thing down one weekend and let him play with it with the telescope. When it was at about that stage that I showed where the feed arm was completed, I wasn't involved in that either, other than one time I did go up there when they were running an experiment to observe, and they started oscillating this thing back and forth, and nothing was happening, and then after a few minutes you could begin to kind of feel, I can kind of feel the handrails wiggling, and a couple of more minutes, it's like, I can feel this for sure. And a couple more minutes, there was a shack where the ironworkers hung their tools and everything and their belts. I looked over in the shack, and all the tool belts were just swinging back and forth. It's like we were in a ship. So I'm starting to get nervous. And John's just happy as he could be, getting his data from accelerometers. Next thing, you could look out and you could see the horizontal feed arm. You could see it moving. And so I'm really getting worried about this time. I'm thinking, like, John, don't we have enough data? So finally, he decided yes, he had enough data. So here's John with Rich Lacoste with their plots, and they were satisfied with. I'll never forget that. I was just thinking, I didn't want to have to call Bob Hall and tell him we broke the feed arm off doing an experiment. But it turned out to be useful data, because he experimentally showed that the damping coefficient was only about 1/2 what they had estimated. They were off by a factor of 2. And so that sent the design engineers, gave them a little indigestion. Another thing was the way the contract worked. The NRAO provided the actuators. Well, the actuators, most of the actuator companies build the actuators to do a vertical lift against gravity. In this case, the actuators not only had to move in a piston motion, they had to resist the horizontal, the perpendicular to the piston motion, because you can imagine that the panels are connected to this actuator, which is connected to the backup structure, and you're shifting it from 5 degrees to 95 degrees elevation. You're carrying the weight of the panels, in some cases, in the plane perpendicular to the piston motion. So they solicited proposals from a number of companies. I see 5 test fixtures here that were constructed to basically exercise the actuators. Here you see two actuators. I guess there maybe is four altogether um, on this rig mounted horizontally, and there is motion put into them through this. There's a cam mechanism here that basically puts side forces on the actuators. Again, I wasn't involved in that part other than just watching, but I think all of the manufacturers failed except one. Um, the survivor was the company that wound up on the telescope today, and you can see this really quite beefy. The actuator is a casting, heavy duty, nice thick shaft. This is the extra mounting for an LVDT that NRAO added. Here you see the arrangement with the what they call the hat bracket and the actuator bracket. This bracket here fit on the backup structure, and it was initially bolted to the backup structure, and these two halves, there was a lot of adjustment between this part and this part, so you could manipulate the position of the actuator. Once the position of the actuator was finalized, they came back and they welded all of this down so that there was no chance of it moving again. The only bolted part would be the actuator itself. The panels sat on these studs, and there's this bushing right here that's threaded on the outside and the inside. The inside threads thread down on this stud, and so to attach the panel fit between these two washers. There was a special wrench that went into the bushing. You could turn the bushing and raise or lower the panel, and then once you've done that, then you needed to adjust this jam nut to hold it in place, to lock it. And so there was a special tool developed. I think Tim Whedon did that when he was doing the panel setting. And also on the actuator, there were special provisions for this stud right here to attach the panel setting tool, which Tim Whedon will talk about more. But the bottom line is all this was pre-designed and built into the telescope way before it ever came down to setting any panels. Now, this is a memo that John was actually the chief architect of this, but I want you to look at the date. This is August of 1992, way before there were even any panels built or anything. But John recognized that early in the project that the specifications called for adjusting the panels to, I think, 40 thousandths of an inch of the true paraboloid. And the corners between the four panels, it was a very loose requirement for the contractor. Well, John realized that we could do better than that, and back in 92, and he proposed a better way to set the panels, including a sketch of how we would use digital indicators and inclinometers and attach it to the top of that stud that I just showed you on the actuator. And there'll be much more about that later. This is one of the more successful parts of the innovation. But all this was built in. So when they were building the backup structure down here, it was built on a combination of hard points that would match the hard points on the box structure, and in combination with temporary supports for the points as they built it out. This was a very, very interesting part too, because these points had to match up the angles and everything with the mating points on the box structure. And it turns out there were some problems there. Um, see, you can see better. There were only a few points that matched to the box structure, and this was built at one angle. I don't remember if this was the bird bath they called it, or I think this was called the bird bath, or it may be the rigging angle. There were two different angles that they used, and so one of the tricky things was the geometry. Every joint in this backup structure is unique. There is a left and a right version of each one, symmetric about the center line. But other than that, every joint is totally unique in order to make it match up to these hard points. The shop drawings to generate these joints drove them crazy. This was a major headache. Unlike most things where you have symmetry and you can build 30 of one piece or something, every one of these had to be custom designed. The story that I heard was that they had a summer student that was really, really good at the geometry and really understood how to do these and could whip them out. Well, comes the end of the summer, they're not finished with all the shop drawings. And the student's getting ready to go back to college. And so there was a panic. This is the way I heard the story anyway. And so they basically approached the student with an offer he couldn't refuse. I think it was something like a year's tuition or a year's college expenses or something to stay over through the fall semester to finish it, which he did. I guess he was probably pleased with worked out for him. But that could have been another major delay trying to find somebody else that could do those drawings. Here you see a little more progress on it. Here we are about complete. Now, one of the things that was also confusing that began to show up as they got closer to the vertex is that while if this was aimed at 90, if this was built at 90-degree elevation, the top chords and the bottom chords would be directly on top of each other. But since it's built at a different angle, you can't use a level to align between the top and the bottom. And so as they got closer to the vertex, is the way I remember it, things got so far out of alignment that they were questioning, like, wait a minute, is something wrong with these joints or something? These aren't plumb. And then it's like, oh, yeah, they shouldn't be. And so then it was like, well, how many of them did we make plumb that shouldn't have been plumb? And so they had to do quite a bit of rework there. Well, then it came to breaking the thing apart in segments and putting it up on the telescope. Originally, they were going to contract with a super duper crane to come in and do that job. But as the project slipped, that crane was no longer going to be available. And you may have noticed it was beyond the reach of the derrick. They could reach half of it from the derrick, but not the other half. And so it left them with quite a problem of how do we get it over to the derrick to pick it up. We could move the telescope underneath the derrick to place it where we wanted it, but we couldn't get the pieces to the derrick. So they had another solution. They initially thought they would put in a temporary guide derrick crane in the center of the backup structure, and from there they would hand the pieces over. Well, when the guide derrick came in, At the same time, they're huge blocks of concrete buried in the ground at various locations away from the telescope that were dead man anchors for the guide derrick. Um, but when it came in, the guide derrick, it had a lot of rust and pits, and the ironworkers threw up their hands and said, we're not going to do this. We're not working with that. Um, you got to do something else. So, okay, they scrapped that plan, sent that thing back to the junkyard, and covered up all the concrete blocks. Um, so then they came up with the idea that they found a smaller crane that was capable, just barely capable of lifting these pieces, a crawler crane. And so what they had to do was break it into pieces. They would lean the boom of the crane over just a few degrees from vertical, pick it up, and then bring it toward the crane. That way they were sure that it wouldn't tip over. In other words, as they moved the derrick, as they moved the boom, the load became more vertical, and so the danger of overturning the crane became less and less. So they could move it maybe 10 feet. Then they had to shore it up, move the crane back 10 more feet, repeat the process. It took days to move each section over to where it could be reached by the S-70. Big time loss. Another interesting thing was how they had to rig these sections. These things were delicate, and they had to be suspended in such a way that when they were brought into place, they were just about perfectly in alignment. So it took a lot of thought on the rigging. You see, one spreader beam that's picking up two other spreader beams that are picking it up at four places. So basically the module was lifted at four places in a particular arrangement. There were come-alongs between the spreader beams and that, and so the lengths of those cables from the come-alongs had to be just right to make it hang in the right way. And of course, everything had to be balanced because, laws of physics require that. So they did a lot of head scratching on the rigging to pick each piece up. Here you see we're about finished with getting the backup structure. That was a major milestone. And it had been over here on this pad. You can see the reach from the derrick could not get to the ones over here. Once the backup structure was complete, then they started building the vertical feed arm. Here you see the vertical feed arm nearly complete, and here's the top of the vertical feed arm over here off to the side. Here's they were assembling the subreflector on the ground. It's not actually on the ground, it's actually about 10 feet up. And the subreflector panels were, again, very precise. Here's a picture of the photogrammetry targets from the ground looking up to the subreflector. I forget the name of the company that came in and did the photogrammetry out of Florida. This is their specialty. They did a very good job of giving the corrections to the adjustments on the subreflector. Finally, here goes the receiver house and the top of the feed arm in place. Another view. The receiver room was added next, I guess, after this part was in. Another view. You can kind of see some of the symmetry. If you imagine the vertex was 4 meters back over here, you can see that there is a radial symmetry back to this point over here. And there is a circumferential symmetry on the top chords. The problem was that it had to meet the weldment on top of the box structure. Going back to that, when they first brought the first parts up, they didn't meet. They didn't match. The hard points on the backup structure did not fit properly to the box structure, and people didn't talk about it too much. But I think what I heard was that there was a foul up between the two design groups in what angle it was being built at, the bird bath or the rigging angle, and so pieces didn't fit right. Moreover, when they started cutting into some of those joints to modify them, they found that inside the joint it wasn't built to the specs. There were some stiffeners that were supposed to be inside those boxes that were not there, and they only found that because there was an error and they had to cut into it to modify some things. So the net result was, to correct that problem took probably a year, added probably a year to the construction schedule. Major problem. Here you see the iron workers were quite proud of their job. They made the newspaper. That's the crew. It's actually kind of a small crew that actually built the thing. Now, I show you this just to as a point of reference. This is from January of '97, and this is comments on the RSI procedure to install the panels. The way that they envisioned putting it on was they were going to put the actuators on. The actuators went up with the backup structure and roughly in place, just bolted. They were very worried about the panels fitting properly. There was a tight specification on the gap between the panels. However, the panels were made on a mold very, very accurately. They were routed, the edges, so that the size of the panels were very accurate. All of this was measured on a coordinate. They had bought a nice Cartesian coordinate measurement machine for this job, and so every panel was measured with a coordinate measurement machine very accurately. So these things were well known, but they were still worried about making it all fit. So their plan was they would line the actuators approximately right, put the panels on, starting in the middle and working out, and set the gap. Then they were going to do photogrammetry of the surface. Then they were going to come back and yux the alignment of the actuators and pin them. And then when everything was just right, then we're going to come back and weld them, all from underneath the surface of the telescope. Well, what I pointed out in this memo is A0043, if anybody's interested, was that they didn't need to do that. If they put all of their emphasis on aligning the actuators themselves before the panels went on, the panels should just fit like a bearing. There shouldn't be any leeway. And so RSI categorically rejected the proposal. Bob Hall was a very big proponent because he saw that he could get something here. He could get a better telescope with the panels aligned with the alignment tool, and if RSI brought them into spec originally, we could cut about 6 months off the schedule. Like I said, they categorically rejected the idea, and Bob kind of got mad with them and said, "I'm trying to help you here, you guys." So, but what they did was they went away and they actually did the test. They actually put the first row on the way I was proposing. And what they found was it worked. That all they had to do was very accurately surveying the um, actuator locations, lock them down, weld them, and then the panels just dropped in like they were like a glove. Like I say, I think it cut about 6 months off the schedule. I'll show you this picture here. This is the only picture I know of where with Lee King on the telescope. Lee King was the chief engineer for NRAO. Over here you have what they call the hot dog stand in the center of the reflector. This is where the instrument guys worked. So the instrument men would give directions to the iron workers on the alignment of each actuator. They'd line it up and move on to the next one. Then the welder would come along and do his thing. These were just stationary. These were stationing places where they could bring the panels up by the crane, put them here, and then they could pick them up and take them out to where they needed them. Um, I believe this is the hot dog stand here. You see a little more of the symmetry of the backup structure here. This is a good view. And again, it had to come down to meet these locations. In fact, it became so complicated to get these joints right. Bob Hargraves had a woodworking shop at home, and he literally went up and made plywood models of what the joints needed to look like, cut them out of plywood, and told the fabricator, "I need one of these." that's how some of these joints got designed. Goes back to John's proposal about the panel setting tool. Tim's going to talk more about that, so I'm not going to go into it too much, but this gives you an idea without the covers on. You had 4 digital indicators. This sat on a stud that mounted on top of the actuator. Uh, my group worked out how to calibrate the instrument, the inclinometers, so forth, and all. Here you see one in place. Another thing was we convinced them to put barcodes on the panels so that each panel was uniquely identified. And so you'd go up and you'd read the panels, and that told you where you were on the telescope and what the inclination angle should be and so forth. I want to point out some things about the panels. Early on, when we were talking about the panel setting tool, RSI agreed to nip the corners off the panels so that we would have access to the top of the actuator stud, put our anchor in. They also agreed to leave these spots on the panels unpainted so that the indicators would actually touch the metal panel and not be thrown off by the thickness of the paint. Then, of course, these holes were for the adjustments of the hat bracket. They had to have access in there to run the brass bushing up and down. There's kind of an interesting story about the paint, though. RSI had decided they were going to use powder paint, which was very durable. And they were quite proud of the fact that this was all going to be powder painted, which would give it a long life. So they put in ovens and did a whole bunch of investment in order to do powder paint on the panels. Well, the panels were built on a mold very precisely and measured with the coordinate measurement machine and so forth. But what they found was they built the very precise panels, and when they ran them through the ovens, the epoxy changed and it warped the panels. So they were kind of sick when they realized that the powder paint was ruled out. They couldn't use that because it warped the panels. So then a whole other uh, level of discussion about what paint to use. There was a lot of concern about the impact of the paint, the dielectric of the paint, how it would affect the microwaves. And so there were all kinds of tests run on various kinds of paint. Um, there was also a lot of concern about sunshine. They were concerned, apparently there was a telescope somewhere that had burned the receiver up when the sun inadvertently passed through over the telescope, and it focused enough energy on the receiver to burn it up. And so there was a lot of concern here about avoiding the sun. And so, to make a long story short, they finally came up with a paint. They announced that they had one that would work. It's called Goldstone 500. And everybody said, oh, yeah, so this is what JPL uses at Goldstone. That's probably a good deal. And it turns out, it says, no, actually, no other telescope has ever used this. They just named it the Goldstone 500 for advertising purposes. Here's just more of the crew setting the things. This is the tool that aligned, this turned that brass piece that I showed you, that brass bushing, and then this turned the jam nut. I think Tim designed that. That's Tim Whedon. Little different view. So you can imagine if you had to come back and working underneath this panel on basically gangplanks under here to yux all this around and then come back and weld it, dragging welding leads and everything from underneath. You can see how much they saved by trusting their surveying instruments. The instrument was good to about 3 millimeters in 1 arc second. It was state of the art. They had the best Leica instrument available at the time. And they gained a lot of confidence. Here's another view. You can see how these things saddled on the backup structure. So we dedicated the telescope, and everybody's happy, and we're finished, but not quite. Immediately, problems developed with the track, and it was not understood. And so they asked the metrology group to help them make some measurements of the track and all. So here's one arrangement where one of the problems is if you want to measure the vertical deflection of the track, where do you anchor it to? Well, you got 4 million pounds on a corner on this wall, and so actually the ground is moving as the telescope comes over. So the contractor provided this for us. They had a scrap beam of steel that they put out here, basically a lever arm that we could use to anchor it back further away from the telescope to put our indicator. Net result, though, you see some drift versus time. I think that's the sun shining on that beam. But here's the interesting point. As the wheel approaches, you see it deflects about 5/1000ths of an inch under the wheel. And then between the wheels, so this would be one wheel, this would be the next wheel, the next wheel, and the next wheel. But in between the times that the wheels are right over the indicator, it actually bulges up. So what is actually happening is, if you look at the side of the track, the wear plate and the base plate are actually being bowed in like an S-shaped curve under each wheel. And in between the wheels, it's actually bulging up slightly. And so you get this tremendous shear force between the two planes. And that's led to the fretting of the wear strip. And there's debate about exactly how much that affects the movement. But you see, so what happens is right here, the track would be depressed, and even between here it's still depressed, but not as much as under the wheels. So kind of an exaggeration. The track would go down, back up, and down, and back up, and down, and back up, and down, and back up as the thing goes by. So one of the problems was that it was designed to support 12 million pounds. And like I said, the weight kept increasing, particularly because of the counterweights had to be added. The specification required that if the bull gear broke off, the telescope would just bob at the rigging angle under the counterweight load. So they wanted to weigh the telescope. So that became an interesting problem. How do you weigh a 12 million pound telescope that's on 4 corners? So what we came up with was, well, first of all, we had to find load cells. We found some 2 million pound load cells and jacks that we rented. And the problem is you've got to lift it until the wheels clear. But the contractor put a limit that we could only move the corner, I think it was a quarter of an inch or something like that. They didn't want to put a twist into those corner weldments. Also, when you start lifting it, the load increases because you're taking more of the load. You model it like a spring. So what we came up with was the idea of we would lift 2 wheels at the time, 1 wiffle beam, and there was fixturing already available to do that. And so we would lift it and measure. This is an inclinometer. We would lift it until we zeroed the inclinometer with it on the track. We did the initial lift. We jacked it until the wheels just cleared, where you could put a piece of paper under the wheels and pass it. We took another indicator, inclinometer reading, measured the angle. Then we lifted it another 10,000ths of an inch or something like that, and got a second reading and the angle. And so if you treat this part as a spring, just Hooke's law, and you could imagine a plot of with it on the track. I raise it a certain amount, take a reading. I raise it another certain amount, take a reading. That should be a linear plot. Well, we had the 2 points with the wheels cleared, and so we took the slope of that curve and backed it back to what would it weigh without the jacks if we didn't lift it. So we took 2 measurements with it cleared at 2 different heights, 2 different angles, and used that to extrapolate back to what it would be at no angle, at 0 angle. And it actually worked out pretty good. We came up with a final number of 16,727,000 pounds with an uncertainty of 30,000 pounds. We repeated each measurement several times and so forth, but the standard deviation for the whole thing was 30,000 pounds. So we feel quite confident that we knew the final weight of the telescope, 16,727,000 pounds. Unfortunately, not all the aspects of the GBT were realized. But I'm going to show you there's a silver lining to this, even the part that wasn't realized. John Finley wrote a GBT memo in which he outlined a laser metrology system, basically have a closed loop system where you measure the surface of the telescope and the position of the cardinal points on the telescope with a laser, and from that you can control the pointing and the surface correction and so forth. This is kind of outlined schematically in a slide Don Wells produced. I'm lifting this from Don. But basically, you've got points on the ground shooting up to cardinal points on the structure, and you've got instruments up on the arm measuring down to points on the surface. And bottom line is this would be a closed loop system then giving feedback to where things actually are. So if the sun's shining on one side more than the other and warping it, you could correct it. And even though the project was abandoned, there's still artifacts probably still around the telescope there, particularly these monuments that people must wonder what are those things. Um, the retroreflectors we had 2004 retroreflectors, one for each actuator, which made a great image. I don't know if they're still there or not, but if they are, just hold a flashlight up near your eyes and shine it into the reflector, and you'll see all these things light up like a Christmas tree. And you might occasionally catch a glimpse of refraction from the sun through these retroreflectors if they're still there. Um, but after burning through $3.5 million of our budget and running out of time, the decision was made to postpone and what ultimately I think was abandon the laser range finding system. Some of the rationale is covered in the documents. We won't bother going through that. If anybody's a glutton for punishment and wants to read it, they can. But there's a silver lining, and one thing is that Associated University has got two patents. One patent for the laser range finding system applied to a telescope, which was later picked up. I'll explain later. Also, we got a patent for a special retroreflector arrangement that lets you virtually measure to the same point from two different directions or two different instruments. Unfortunately, neither of these have been commercialized yet, but I think they will eventually. However, Bob Bridges at what is now Faro Technologies, he was the chief scientist, or is the chief scientist at Faro Technologies. He became aware of this work through the Review of Scientific Instruments publication as well as the patent. And they were making laser trackers. These were basically interferometers that measured relative distance. They could not measure absolute distance. They have to count fringes. And so if the beam gets broken, you have to start all over again. And they recognized the merit to the system that John Payne, the architecture of what John had designed, what we call phase measurement. And so they decided that they were going to go into modify their laser trackers to offer this as a feature. They weren't sure how many people would want it, but it turns out that's their whole product line now. They don't make the interferometers anymore. These things are used extensively in the aerospace and shipbuilding business. So even though the NRAO effort was, as I phrase it, it was too far ahead of its time. Even though that was the case, it has been commercialized. If you look at the Faro patents, and I used to work with Bob. I worked with him after NRAO. They had already built this. This was after the fact. I did not work on the instrument designs with them, but the basic idea of John Payne's architecture of phase measurement, modulating the beam, and recording the phase, they capitalized on and commercialized it into a very fine instrument. Now you can just go buy these instruments for like $80,000 a piece. So if at any point an observatory wants to implement something that was like what was envisioned by John Finley, you can just go buy the instruments now, and it's just an engineering job to apply it. And with that, that's the conclusion of my presentation. Like I say, a lot of this is the way I remember it, which may or may not be accurate. So if others see anything here that they disagree with, or that I've got wrong, please drop me a line and tell me what I need to change in case they ever do this again. Um, and if you have any questions, feel free to contact me. My email address is here on the slide. I would like to hear from anybody if you've got any comments or suggestions. Thank you.